realize that this is really reconstructing line density epsilon. We take epsilon to 0, we're left with a rational term that we're interested in. So that's the role of the dimensional regularization. And so we now want to move on from unitarity to generalized unitarity. So far we've been picking out contributions with two propagators. We've been insisting that there be two propagators in every contribution. You might wonder, why not insist on more? Can we cut more lines? Instead of just cutting 2 lines, can we, for example, cut 3 lines? So that would be our ordinary unitarity cut. Now let's cut a 3rd line. Well, what would be the advantage of that? Well, one advantage is very clear. If you cut 3 lines, you can't have any bubbles. So we don't have to worry about removing the bubble in that channel. Moreover, once you cut 3 lines, instead of having multiple triangles, so having, let's say, some combination of 1 and 2 matched triangles, you'll only have a single triangle. You'll still have boxes, but there'll be fewer of them because there's fewer boxes that share 3 propagators compared to just 2 propagators. And do we have enough degrees of freedom? Well, we're essentially, as far as the cutting is concerned, so if you think back to how we were doing things yesterday, then the algebra and the structure of the propagators were treating in 4 dimensions. The loop integral we're then doing in 4 minus 2 epsilon divisions. So in 4 dimensions at one loop, we have 4 degrees of freedom. There's 4 components. There's 4 components of the loop momentum. The loop momentum L. So in fact, we can imagine not just cutting 3, but even 4 propagators. And that would be very nice, because then, in fact, if we were able to do that, we would have no triangles at all. We just have boxes. And in fact, we'd have a unique box, because there's only one box that has 4 specific propagators. So then we'd really be getting a step closer to picking out a single element in the sum, and assuming that we can do something with that expression, the quadruple cut, we'd be directly extracting the rational coefficient of that box. So let's go ahead and do that. The question of infrared singularities, we already know that by then taking the loop integral into 4 minus 2 epsilon dimensions, we can control all of that. So we have brought down our box integral. And again, just as a notational device, let me remind you that Ki dot j is just the sum of momenta from I to j. So K12 is K1 plus K2, for example. Okay, so we saw last time how we do cuts. We replace propagators by delta functions. So let me do that. And let me be a little bit sloppy about factors of I and 2 pi to the 4th. Just cross that out and really just focus on the delta functions themselves. Okay, so we know about delta functions that what they're trying to do is they're trying to localize the integral. We have so the integral over a delta function is going to constrain each of the components to solve the equation. We have 4 delta functions, so there's 4 simultaneous equations that we need to solve. Yes, the plus is I'm just copying what we did last time, getting the preponderant energy. And if you're a little bit puzzled by that, just hold that thought for a few minutes. We learned how to do a cut, and I'm just blindly applying that idea to extending from 2 to 4 cuts. So the question is, how many solutions do we have? We have 4. And it turns out that the counting solutions of multivariate polynomial, higher degree polynomial equations is actually a fairly non-trivial thing to do. But here we can observe that we can take linear combinations of these equations. For example, we can subtract this one from this one. That's going to leave us with an equation that's only linear in the loop momentum. And likewise, we can subtract the original form of the second equation from this one, and that will give us L dot K2, S12 minus K1 squared equals 0. And again, here we can use momentum conservation, and then subtract the very first equation, and we then have three linear equations and one quadratic equation, and in this case it is easy to count. We expect two solutions. Let's actually solve the equation. Solve these equations. Let's do it explicitly. And let's do it explicitly in the case that legs 1 and 4 are massless. So we know that L is going to have to be a massless vector, so we can write down the general form of a vector like that. Let's see here. We can use our spinners to write down a null vector. And this is a nice choice because, of course, the first equation, the second result, is automatically satisfied. If we dot it into K1, and then we see we're going to get an angle product of 1 with 1, so that'll automatically be satisfied. If we dot it into 4, then we're going to get a bracket product of 4 with 4, so that's automatically going to be satisfied. And we have one more equation that we can impose. It's the third equation, and when we impose that equation, we'll find that S12 is equal to C over 2 times 1 to 4. So we can then solve for C. If leg 2 happens to be massless as well, then we can further simplify this result by dividing out by the angle product of 1, 2 on both sides, but that doesn't really matter. In any event, we have a solution for C, and we would find that our vector is, let me write it in the form that, so we have S12 divided by 1, 2, 1, 2, 4 times 1, 2, 4. And similarly, there's also going to be another solution, which is given by minus S12 over 2, 4, 2, 1 times 4, U, 1. So we have our two solutions. Okay, so I got K2 into here. That gives me 1, 2, 4, and that thing is supposed to be equal to S12. And that's what this is, the normalization C. So we have two solutions, but there's a problem. The problem is that, of course, vectors 1 and 4, and therefore spinors 1 and 4, they're completely unrelated. They're certainly not complex conjugates of each other. That means that these solutions are complex. But the domain of integration here, just ignore the plane and IS1 for a second. The domain of integration here is the real slice. Components of L are real. And if we think about defining a delta function as some delta convergent sequence of Gaussians or Lorentz or 1 over x squared plus a squared type functions, then if we plug in a complex value here, whatever the way we define the delta function, we're going to get 0. In fact, the notion of a positive energy, I mean, what is a positive energy when the energy is complex? It doesn't mean it. So we have our two solutions all right, but they don't lie in the domain of integration of the delta function. And so this quadruple cut is going to give us 0. And ultimately, if we were to apply it to the other side of the equation, we also get 0. So we would derive a true equation, but one that is not very useful. So what are we going to do here? Well, it turns out that the right thing to do is to ignore this problem, essentially. That's the way it was done originally. And just pretend that the delta functions are allowed to have complex solutions. Actually, that turns out also to not be correct when you go beyond one loop. So what we really need to do is to reinterpret what we mean by the delta functions and what we mean by cutting. And the way we're going to do that is we're going to replace these delta functions by complex solutions. It's really the more natural kind of object. The way you localize an integral in a complex space is not by imposing a delta function, but it's by doing a contour integral. Because when you do a contour integral, you're essentially picking out the value of the function at the pole. You're localizing it at the pole. So how does this work in one dimension, one complex dimension? We have some contour integral. And it's going to be a little circle around some point, which I'll call Z0. That means I have some circle of some small radius, delta. I won't be very precise about what I mean by delta here. So we notice that if we do a contour integral like that, and let's suppose we have some polynomial indices right here, you can see in the numerator, and we have polynomial 2 in the denominator where this equation has only a simple root at a, so the definition of C0 is to this equation so that this object in fact has a simple pole, this denominator has a simple pole at C0, so we want the thing to go essentially going near values of a, near C0. So we know how to do this integral. We're simply going to get the numerator evaluated at C0, and we're going to get a Jacobian in the denominator. So remember that if we were doing a delta function, a real delta function, delta of f of x, then we're going to get, of course, the sum over the solution of f of x equals 0, and we're going to get 1 over the absolute value of f prime of x where that solution happens. So the very crucial difference here, that crucial difference is the absence of the absolute value sign here. There's no absolute value. You do a contour integral with an analytic function, you get an analytic function. And it's actually a crucial difference, and this is actually the correct way to think about it, and not this one. So you could imagine having some complicated definition of a delta function that extends into the complex plane and all that, but that's not what you want to do. You don't want those absolute values. So when I write down a delta function now, then what we're going to do is define what we mean by the delta function. So this is a new kind of complex delta function, no positive energy condition, and we're using the same symbol as we would for a real delta function, but what we mean by this is this contour integral around the solution of the same numerator and with a denominator that localizes the integral at the pole. So when we do this, we now have to do this not in one complex dimension, but in 4 complex dimensions. And the theory of multivariate